So,
Okay.
Okay, on you go, Neil.
Okay, wonderful. Okay, right. Well, good afternoon, everyone. My name is Neil Jones, and I will be your facilitator for today's webinar. I'm here to assist my colleague and friend 𝗚𝗽𝗄𝘆, who represents Oxford Well Engineering, OWE, a London-based company that specialises in well engineering design and drilling optimization. OWE has been operating for over 7 years and serves a global client base, including major exploration and production companies. Today's topic is how to achieve superior well designs and optimize drilling for deep geothermal wells. Next slide, please, Naeem. Both of our speakers today are experts in geothermal well design and drilling. 𝗚𝗽𝗄𝘆 is the Managing Director of OWE, holding an MSc in Petroleum Engineering from the USA. He has over 23 years of global drilling experience, including geothermal wells, and is a recognized coach in advanced drilling and digital drilling optimization. He is also a visiting lecturer at the prestigious University of Leoben in Austria. Dr. Thomas Miyora is the Chief Geothermal Engineer at Kenya's National Geothermal Drilling Company, GDC. Dr. Miyora is a renowned expert in deep geothermal drilling with over 18 years of experience. He has led drilling teams and delivered over 80 high-temperature deep geothermal wells in Iceland, Japan, and Kenya. I will now hand over this to 𝗚𝗽𝗄𝘆 to begin today's webinar.
Thank you very much for the introduction, Neil. Just maybe we can, talk about this agenda that we have for today. This agenda is divided into 3 different parts. One is the geothermal well design. So we'll be focusing on the well design. And a lot of it is actually around the data-driven well design optimization as well. So I think this could be like a whole circle for designing those geothermal wells. And a second part of will be digital drilling optimization, how to actually ensure that you are optimizing the drilling operation using the kind of leverage of the digital technologies and the way to improve them as well. So it will be just talking about how to improve the actual construction of the well to enhance the cost saving side of the things. And the last part is kind of more interesting. It will be actually taking a base case for a geothermal well, and we will be running through the software and using the software as our tool, trying to optimize the design as we go. And for that one, I have 2 different applications that I would like to use. One is the trajectory design for the geothermal wells. And we will be aiming to make the well shorter, easily drillable, and to kind of improve the kind of side of the thing that actually make it quicker and easier to kind of drill those wells. So second kind of application that I would like to show would be around the well design itself, the well engineering simulations. And we will be talking more about it once we get there. So I think I'll not spoil the kind of surprise there. So this 15 minutes, the last 15 minutes will be very, very interactive. We will be showing you around into the software environment, how people actually go around the software. And the goal will be not to actually just simulate the things and just to come out with a trajectory that is okay. And we are talking about actually improvement, as we go in the steps. And we will also talk about a course, maybe just a single slide or something, just to show you the kind of course that we would like to offer. Currently, we have few people already signing up for that course. So we will just flash maybe just a single slide about that particular course. That is the course is a practical training actually. And it will not be just theoretical, it'll be all design based with software and everything included. So we will also have our short QA session, question and comment, and we will take your question as well towards the end. And now I'm handing it over to our friend, Dr. Miyora, who is subject matter expert in geothermal. And he's a chief geothermal engineer for a national oil company in Kenya. Okay, Mr. Miyora, yours.
Thank you, Engineer Naeem. I will start directly in the introduction part. Geothermal. Geothermal, as we know it, is a source of energy from the earth. And the world, as we know it currently, is moving towards green energy due to climate change and global warming. So there are many sources of green energy. But today, in our webinar, we will focus on geothermal, specifically drilling and optimizing, and on how to achieve the best well drilling and in the shortest time possible. But before that, I just want to give us a short background concerning geothermal. Geothermal, as we know it, is the vastest source of energy, yet it's kind of least tapped. Everywhere you go, you will get a form of geothermal. Some are high temperature, others are low temperatures sources. But all in all, we have geothermal almost in every part of the world. The map on your right shows hotspots where high temperature geothermal sources are found. And these are near tectonic boundaries. So the map shows several countries that are endowed with this resource. You know, famous countries like Iceland and New Zealand, Indonesia, Italy, Kenya. They have exploited this resource in a big way. In Africa, you can see that in the central part of it, the potential is just very, very big. But the one that has been utilized and exploited is very small. So if all geothermal resource was to be exploited, more than 50% of the energy will be supplied by geothermal for the central part of Africa. Next slide, please. In developing geothermal, there are various stages. As you can see on your left, we can identify around 4 stages. The first stage is developing period, and this one is related with determining the presence of the resource. And the first step is always reconnaissance, kind of looking around or studying aerial maps, field study, just to ascertain that there are signs of this resource. After this, if the signs are very good, then exploration is done. And this is either surface exploration or subsurface exploration. Usually we start with surface exploration and then we move to subsurface exploration. There we'll gather a lot of data, and this data is used to model the field. And then after modeling, well sites will be identified, especially where we have upflow zones and there's a source of heat. This is the points where wells will be sited. Now, after confidence has been built on the model, then exploration drilling is done. Usually 1 to 3 wells are drilled, and this is for the purpose of proving the existence of the resource. Then after exploration drilling, if the resource is available, then we have what we call the appraisal drilling stage, where the field is marked. The expanse of the resource is studied, and more scientific studies are carried out. And at this point, the size of the resource and even the size of the power plant is designed. Now, the next step is feasibility studies and production drilling. This is where a given number of wells are drilled, dictated by the size of the power plant. And at the end of the development stage, you will have a power plant. When you have a power plant, you have some kind of a plateau. The good thing with geothermal is that when the power plant is on, you have operation and maintenance, and it is usually very basic operation and maintenance. And then you just keep generating money for a long, long period, even up to 50 years in a given field. Then if the resource is utilized, of course, we don't have perpetual resources. There'll be declining stage. This is a stage where we'll think of maybe retiring our fields and then letting the resource recharge. From the first stage of reconnaissance to the power plant, it may take somewhere between 10 to 15 years. But I know of places where it has taken about 5 years and electricity is generated or the direct use of the resource is applied. Next slide, please. Now, when it comes to geothermal, wells, they are closely related to oil and gas wells, but the major difference is about temperature. Geothermal wells have very high temperatures, over 150. There are wells which you can get even temperatures to the range of 400 degrees Celsius. We also have a difference in the formation type. In oil and gas, majorly it is sedimentary kind of formation, but in geothermal, it is volcanic rocks, which are very hard, highly fractured. And when it comes to drilling, sometimes it is difficult because you experience serious losses, and then sometimes downhole problems such as stuck pipe. So this calls for us to do thorough design, thorough optimization to ensure that we drill these wells in a safe and in a cost-effective manner. When you look at oil and gas wells, the drilling is usually smooth. I think given the number of years of experience that they have been drilling compared to geothermal. Please, next slide. When it comes to the architecture of the wells, oil and gas wells, their architecture is kind of complex, and especially the completion part, because we may have tubing and sometimes pumps and all that. There are many types of casings. You may have tieback casings, sometimes intermediate casings, of course, depending on the characteristics of the field. In geothermal, especially when you're exploiting the resource for direct use, for example, brine for heating and all that, the architecture is a little bit complex, but not as complex as that for oil and gas. You may have an electric submersible pump in the well, in the design, and also a number of casings. We usually have around 5 casings in geothermal, and it's kind of generic. When we're exploiting the resource for electricity, the architecture shown on the extreme right is usually utilized. And the casings are usually cemented all the way to the surface, starting from the surface, the intermediate, the production. The only casing that is not cemented is the liner, which is usually perforated. So for geothermal, because the resource is usually of high temperature, that's why the production casing is usually cemented all the way to the surface to ensure that we have integrity in the architecture, to ensure that there is longevity when you're utilizing the resource. Please, next slide. Typical geothermal wells architectures are as shown. You may opt to drill large diameter wells, whereby you complete the well using a 12¼ inch bit, and the liner casings is usually 9 and 5/8 inch. Most of the geothermal wells that have been drilled in the world are of regular diameter wells, whereby the production hole is drilled with 8½ inch bit, and then the liner casings are 7 inches, and they are usually perforated. The slim wells are very few, and they are usually drilled for the purpose of either getting data to help make a decision whether to develop a geothermal field or not. Sometimes these slim wells are drilled, especially if we want to utilize the resource for direct use, such as brine for heating and all that. but they are not as common as the other two. Next slide, please. Now, if we look at the cross-section in the world, the kind of casing architecture that they choose, in Iceland, they usually have both large diameter and regular diameter. That is 12.25 inch production hole and 8.5 inch hole production hole. So those ones, depending on the characteristic of the field, they choose either of the two. In the US, they usually have large diameter holes, most of their wells, geothermal wells, but of course they usually have also regular diameter wells. In Italy, Indonesia, Japan, and Mexico, and Kenya for that matter, we usually drill many of the wells using the 8.5 inch bit at the end of the well. That is the production casing, and then we run liner casing, which is 7 inches. So as you can see, the decision to either put large diameter well or regular diameter well, regular diameter casing depends on the characteristic of a particular field. Let us move to the next slide. When drilling, we usually do monitoring, and the best monitoring parameter that we use is the depth versus time curves. On the extreme left, these are wells drilled in Kenya, 𝗚𝗽𝗏, the famous 𝗚𝗽𝗏. And these wells, they started drilling these wells way back in 1982, but the ones shown here were drilled in around 2006, and they had quite a good experience in drilling. The average drilling time, as you can see, is around 50 to 60 days. The longest you can see there is around 90 days. The next field to be developed in Kenya is Menengai. And this field was very problematic, especially in the initial stages. There were many problems downhole. And the source of heat was kind of very shallow. There is a well that I know we drilled and encountered magma. So there were many problems. But with time, we came to learn the characteristic of the field, and we managed to drill in a short time of around 60 to 70 days. The extreme right graph is the newest field that is being developed currently. It is called 𝗏𝗏, and as usual, the starting point of drilling is usually problematic because this is the learning stage. But with time, the graphs on the left, we come to learn about the field, and then we do design optimization, and then we achieve a better drilling time as shown. So learning, of course, we are still doing more optimization on this field because we are on the production drilling stage. So this is my interest in drilling, optimizing drilling to ensure that you hit your target at a cost-effective manner. Next. Now compare the geothermal wells, the curves. The curves in geothermal wells are very rugged, many flat spots, serrated. But for oil and gas wells, as you can see, I got this curve, and many of the oil and gas wells are usually smooth, and it's like straight to the point. If it is cementing point, very smooth cementing, drilling, very smooth drilling. Because of this experience, we want to get the experience from oil and gas and utilize it, adopt it for geothermal drilling to ensure that we drill in this kind of manner. You can see that in around 40 days, they have already hit the target of say 3,000 meters, in contrast with geothermal, which takes even 100 or more days. And finally, next.
Yeah, okay.
Finally, Naeem, please, you can take over.
Yeah. Yeah, I would like to maybe just show you a study just along the same line as Dr. Thomas has just mentioned. The geothermal well has got completely different signature for time and depth profile. And when you're drilling the geothermal wells, you can see them right here. There was a study done in Colorado, and for the same shape of the well, same footage and everything, it is showing that it will take 3 times more time. And also look at the kind of character of the lines. It is showing a lot of step profile. Step profile means they could not drill smoothly. And also it is showing these humps. The humps are indicator of stuck pipe and sidetrack. Very, very big flat times for geothermal well. Flat time is a bad news. Flat time means you could not drill for whatever failures or whatever issues. Humps are even worse because you have to get, actually drill the section again. You stuck. And looking at this, you can clearly see the oil and gas wells are going fast, very, very quickly to their target depths. And the one in the rectangle are the one that will take forever. When they are drilling, they are not really properly drilling because you can see the step profiles and a lot of side tracking going, which is not ideal because you can get stuck because of the losses that usually come with it. So what is the reason for all these issues? Why they are so much different miles apart from each other? And the reason actually is multi kind of factors. Basically, there could be a lot of factors. Something will kill off the fun of the geothermal well drilling. It could be the hard formation. It could be the smaller rig. And I think what I find very, very surprising is not able to learn from oil and gas. A lot of these geothermal wells are drilled by the project managers. A lot of people take it as a project management kind of thing that people have certain experience and they just use it. How about using 150 years of this oil and gas industry experience? We got all kind of complex well. Some of them are similar to geothermal wells, very hard drilling. You got stringers, got a high temperature and things like that. But we did not see that synergy of having these expertise into the geothermal. So without going too much in detail about what actually caused this problem, because this is a separate presentation, probably somebody has to do the study to find these out. But this is all around the world. When I did my geothermal wells, we estimated the time to be 2 months, 2.5 months. It was in EU. I'm not going to mention the name of the operator. It was one of the biggest there. And we thought it will be finished in 2.5 months. Unfortunately, it lasted for more than a year. That was a little bit surprising. They have a lot of stuck pipe, a lot of drilling them again. When they got to the target, they found there was no hot water there. It must be a wrong target, probably. So there are a lot of interesting things that could go wrong, and you end up drilling for 1 year, even more. So this is the worst possible case. And I think I would like to maybe show you a small workflow that has been used. It's not a rocket science or anything like that. It's not too complicated. Let's have a look at workflow that you can use to tidy up the ends, and then you can win at the end, and you will not have so many surprises with the geothermal well. Okay, this is the workflow I would like to show you. It's a geothermal well design optimization roadmap, or let's say just a kind of loose fit, flexible roadmap that you will remember. Even after this meeting, you may remember because there are not too many things to remember. So the first thing is the conceptual well design. When you receive the BOD from your subsurface team, you can start constructing your geothermal well design. It could be design A, design B, design C. You got few of those designs. And at the same time, now you know the depths of the reservoirs, you know certain ideas around the location. You may be able to think about what kind of rig do you need. There are now in these days, we have small rigs, but small rigs does not mean bad news. Some of the small rigs are robotic rig, very, very fast, smart. Everything is digitalized and everything. Fantastic rigs. And they drill doubles, only 60 footers or 64 footers. I have run into those, they're very impressive. So you can actually choose the rig. The problem with very small rig, it cannot lift too much. So you have to think about the highest loads and things. So there's a very nice, let's say, collection of information that you have to do and get it right at the very offset, start of when you are putting the bits and bobs for your well design. You have to come up with the rigs and where you will be drilling from, and how far that is from people who live around these areas, because some of the areas very populated with people. Here in the UK, they had to shut down drilling for a couple of times for some geothermal wells, by the way, because the local complained that they are feeling vibrations and their dog cannot sleep or something, something funny like that. But of course, it matters. It really matters. If people are not happy, you cannot drill anything, even a foot or a meter. So you come up with the designs and start to look at the rigs and where you will be drilling from, which areas are no-go, which areas you can drill from. You have a feel for, then you can draw circles on the Google map that these are could be my possible surface locations. And then you will have a feel for the target. Once you know the surface location, you know the targets that geothermal subsurface team has given you. You can actually start thinking, drawing some trajectories. When you draw the trajectories, you also draw the casings on them. That's a kind of standard flow. Everybody can do it. Most people can do it. Once you have the conceptual well design, few of them maybe, then you go about selection of the well design. This is where the mistake happened. When you select the well design, you firmed up the cost. You firmed up the risk profile. You firmed up the deliverability of the well. You firmed up a lot of things that should be in the right side of the things. If you were to be successful, we need to select the right well design, the design that delivers everything. And how would you do it? There is a kind of Excel sheet people use sometimes. There is a workflow for jumping from several design to one selected design. There is a workflow for it. If you want to speak in layman's term, it will be SWOT analysis, strength, weakness, opportunity, and traits, or risk, if you want to call it risk, SWOT. So you will draw a map of strength of your design. Each of these design that you have in the first step, you will come out with their strength, their weaknesses, what opportunity do they offer, and what risk they present. And then you will have a checkbox list, tick box, green or red. No, it is not good enough, too much risky, it's not delivering, things like that. At one point, you will have a well design that delivers everything that you are expecting it to deliver. It has got more strengths than weaknesses. And then you can select that design that way. There could be a separate presentation on it. Actually, it's so important. But anyway, for this short webinar, we will stop this one right there with this explanation. Then you go for the detailed well design. You will say, I selected this design. Let's open everything up about this design. I did not do casing wear. Let's do casing wear. Let's do the other stuff. Let's see if we what will happen if I lose all my fluids. What will be the situation if certain things materialize? What happens if I do not find the reservoir? Can I go to some other subsurface targets using this design, the same design? Then you apply all kind of scenarios and reality checks, and you will bring in the expert guys who do the kind of nitty-gritty of the things to make sure that your design will not fall apart. Unfortunately, this detailed well design, people say whatever we have done in the past had been working. Don't fix it if it is not broken. In reality, if you have a mistake in the design, you keep copying them in. Selection of technologies, selection of drillings, all kind of things, you keep copying them, the mistake multiplies by itself if you don't do optimization. Some big company now, they call this detailed well design as well design optimization phase. In reality, they want to test it and then optimize it. So there could be two parts to this detailed well design. Okay, so Anyway, so you checked it. It stand all the tests. It stand all the scrutiny, all the modeling, all the what if scenarios modeling. It passes. If it does not pass, what are you going to do about it? For example, later on you find out, okay, we may be drilling more footage because the reservoir could be 200 meters deeper. Are you going to go back to the select phase again? Probably not. You may strengthen up your design, modify things to it. If your rig cannot handle this extra footage, maybe you need to change the rig to make it happen. The most important factor is to deliver the well according to the specification. Otherwise, there's no point drilling. That's what most people don't get it. You're not here to drill the well as fast as possible, get to the TD and look great. We want to construct the well for longevity, to make it last for 25 years without failures. With geothermal well, this had been a problem. They tend to fail prematurely. In a few years' time, you may have a workover. Who will pay for the workover? It will be a problem to find finances, and maybe there are issues. And so it's a very important thing to get it right first time, because all you get out of it is hot water. It pays for itself in 10 years' time. Oil and gas pays for itself in 4 months, 6 months. I've been on the well. It had a lot of failures. It cost us $90–80 million. People were laughing when we finished it. They say, great, we will get paid in 6 months time. Anyway, what's the big deal if it is so expensive? But geothermal is not like this. We need to make them cheaper and stronger for this reason alone, that they pay back slowly. Okay, so anyway, you will write the program based on what you have found, what are the mitigation strategies of certain risks. You will have a plan of everything and very, very diligently explain all the T's are crossed in there and procedural kind of program that you need to put in. If you don't do that, when it goes to the rig, when people are implementing it, they will be in trouble because they don't know at what step something is missing, what they have to do. Then experience comes in. If they have, if they do any mistake, then there's a problem. So you need to open it up in terms of procedural details. Okay, so you write the drilling program and then pass the ball. Pass the ball to the operational drilling team, which is on the other side of this dotted line. This is two different worlds. One is a planning world, one is an operational drilling world. You need to somehow find a way to synergize them, make them run in harmony. I have seen in my time, 23 years of doing this, they have all kind of plans and everything, and wells just did not go right. If you did not do the planning right, what's going to happen to the drilling part will be nightmare, basically. For example, if you have a bad trajectory, you set it up because you have a well planner, did not have enough experience. They do only the pictures and drawings. They don't know if this trajectory is the best for drilling. Somebody approved it, and there you go. You have a problem then, because when you try to drill this well with this trajectory, it may fall apart. You may have a stuck pipe. You may have a hole cleaning problem. You're fighting with the foundations all the way for each of these sections or some of those sections. You end up with expensive well. Some of the design problem comes into action when you are drilling it, because you are working with a bad design. But most people don't realize it. They say, oh, actually we had this trend wreck, very horrible drilling. We got stuck a few times. It was hard to run casing. A lot of it could be tidied up in the design phase. That's the key that I would like you guys to remember. When you do the planning, plan it for drilling. Okay, this is critical there. If you have wrong WBS model, wellbore stability model is not fine-tuned and correct, you will have all kind of problem will break loose. Okay, and then you will have huge NPT failures, stuck pipe and everything. If you have picked up the wrong rig, it cannot handle certain kind of technical limit, it's breaching the limits and issues happening. What are you going to do at that point? You cannot stop drilling now because the rig is already there. You'll be surprised there are some incidents where people have to stop drilling geothermal wells and they ask for different rig because they cannot drill this anyway. So that's that kind of planning. So spend a lot of time on planning, but not for virtue signaling that I'm doing a good plan. Get the field guys in along with you so that you guys can work together. Ask them if it is doable, not doable. Is it easy? Is it hard? That way you can have a team that have the grip on the realities. So those things you have to be very careful with. Okay, I'm a little bit tight with the time. Sorry about taking too much time on this slide, but this is the main slide for how would you go about optimization of the design. Best practices are everywhere. When you look for the best practices, for me, only one best practice, just one best, make it good for drilling and deliverability. The first thing, the second thing actually more important. Does it deliver everything that you ask for? Is it easy to drill? Second question. And you need to make it happen. All the designs you have, you must calibrate them because design, anybody with the software can do it. You need to calibrate them and it should be calibrated to a degree where you can actually almost showing it in reality. It looks like almost real. When you apply your design to the past well, you can actually predict problems that you have seen. That kind of calibration. And they are not hard. It's just a certain workflow that you have to follow. Okay, so I will go quicker. Again, this part, I would like to give you a roadmap for well cost optimization. This well cost optimization requires a lot of digital input. This roadmap that you're looking at is telling you the first thing you do with any well design is to inject it with a digital offset analysis outputs. You perform the digital offset analysis, come out with, I have mentioned the list here, which is telling you all the failures, all the issues, everything around the design problem, operational problem. You find out the root cause using the digital expertise. When I say digital offset analysis, they're completely opposite of what we know of about offset analysis. You're not going to read all the reports and DDRs. You are actually creating the whole well, the wells of interest, the failure envelopes and everything, and come out with root cause and room for improvements, operationally, design-wise, what was the invisible lost time and everything. And then you feed this into the funnel of planning. That's what you do. These tick boxes, the red one means very, very data intensive. Red one is all about the data. The black tick box, you will use it for calibration and other stuff, but not huge lot of data. So this is just showing you the kind of path that a good geothermal drilling engineer should follow. And if you work in oil and gas, believe me, this is almost the same, basically. It's just a common sense that you need to leverage the data, combine it what you do normally, and use it smartly. Don't waste too much time because data needs special expertise as well. So well cost optimization, everybody say that needs to be low and better. I will say you need to increase the cost of the well if you have to, in the favor of well safety and integrity. If the wells are not safe or the integrity is compromised, increase the cost, make things stronger, not just dropping it like this, because there had been some operators that drill few wells. In few months time, most of their well had well integrity problem, casing pressures and things like that. They were up due for the workover, they could not produce. They were very cheap well, by the way. They broke the records. It was in the news that they broke the record of doing it very fast. Planning was fast, delivery was fast, they drilled to the TD fast, all the sections were fast, except that in few months time, nothing happened. They have to shut down everything. That's the wrong way to optimize, by the way. Okay, so why bother about digital drilling optimization, which is how to construct the well with digital empowered technologies or infusion of these digital things? Because if you don't do it, you will be actually costing 20% more rig time. Usually the geothermals are drilled with doublet, 2 wells in one go. First well, injector or producer, and one after another. And if you do it with the proper digital infusion in the design as well as drilling optimization, you will save 20% of the rig time and everything will be quicker and you will be quite assured of the results. This is the chart is showing the green bars are showing you the normal cycle of drilling campaign. If you bring up a rig and drill 10 wells, this is the cost and the number of days it goes. Similar shape, similar everything. You learn from drilling curve. And the purple one is the one that digitally infused designs and digital drilling optimization. When you use them, you start low because you have already retrospectively solved a lot of problems. You start with a strong footing. And for 2 wells, for example, this is the biggest difference because you only drill 2 wells for geothermals. So you need to be on the top of it if you would like to reduce the cost. Okay. So this is just a kind of slide that tells you what is in it. If you are going digital and doing the drilling optimization, I'm not going to stay too long. I will send you the slides. What it requires, how would you put this together? There's also, of course, the common sense. You need to have the management, right people, and you do not let only the drilling people, drilling service company to do the job for you. If something is failing, they're not going to tell you. So you need to have your own self or maybe a third party small companies and similar things. Everything is a sort of common sense, especially with a lot of automation going at the moment. You need to be watch out of automation. Some automations are too simplistic. They will look nice on the visualization side of the things, but they oversimplify and then you end up with wrong decisions. So I'm going to skip that one. And you can also, by the way, this is also very important to understand that you can actually do the real-time drilling optimization from your PC, from your own computer. You don't need a real-time center. You just need a workflow and the software and the models and things like that. You calibrate them. And when the drilling comes, you can take charge. Anyone can take charge. And when the drilling is not on, you can go back to your normal job. There's no need to spend so much money on setting up a big real-time center unless you are a big company, unless you have like a lot of wells being drilled and stuff like that, then you can do it. But for your small, you can do it at home from your own, but you need to get the models right, which we can show you if you would like to see this. Okay, so let's go to the model. Very simple model. It's been going for last 30, 40 years I know of. Data comes in real time. People look through and they do their real time engineering. They find the trends which are not matching, abnormal kind of trends and abnormal events. They catch them through the data. The data is plotted against the model. What is ideal, what is happening should be very close to each other. And it is that kind of in a simplistic course, it will be very easy to say, but all these things, then you feed it back. If you find something wrong, then you feed it back to the drilling team. Drilling team sort it out. They call the rig or you call the rig. Depends upon whatever you guys have agreed. That kind of things had been going in very big operators' offices. The model is almost the same. Only thing that's different is how you communicate to the rig so that they can do something different. Okay. So I'm going to take you to the kind of interactive session. This is going to be quite interesting. As I said, for the interactive session, I have put together 2 different models. The first thing will be you look at is the easy one, the basic one, the trajectory. Trajectory is the backbone of your well. Your design is riding on the top of this, of the trajectory. If you have a slightly longer trajectory, you'll be drilling for no reason. If you have a crooked trajectory, it will get you into very costly situations. And then you have a design itself with casing and everything defined. Now you want to check out with the modeling if it is okay to drill, if the hydraulics are okay and the torque and reg. So let's go with the first one. I'm going to stop sharing and bringing you the software interface. Okay. Okay, let's bring in the software I have. Okay, so I think this will be the right one. So this is the software. This is 𝗚𝗏 Well Seeker Pro, by the way. 𝗚𝗏 Well Seeker Pro is the kind of market leader for a lot of things. One of them is their flagship, this Well Seeker Pro. They have around 3,000 licenses around the world. A lot of companies that I have worked with, they use them. By the way, so this is their software. It is showing you the red trajectory that somebody designed as draft A. It's just a draft. They say this location, if I drill from this location, I will hit my target. It will be 4,900 meter or 5,000 meter, just to be kind of round number. And then somebody say, okay, maybe we don't need two build section. It's got two build section. One build section and two build section, very long tangent. Can we tidy it up and maybe bring it close to the target? Somebody said, okay, let's bring it to the blue one. This is my iteration 2. 200 meter saved, 250 meter saved, because you are closer to the target. You don't have to do too much drilling. And somebody came in and say, actually, we don't need a tangent. According to the requirement from subsurface, we can kick off deeper. All they are interested in is this goes to kind of in the form that is like 55 degrees at the target, which you can achieve even if you go deeper and kick off deeper. You come close to the target and make the well even shorter. So the difference between red and green is 500 meters. You were drilling 5,000 meter with red. Now you will be drilling only 4,500. This is a simplistic case. What you do in reality is you ask for all the constraints. Where can I kick off? What will be the inclination through certain formations? What inclination do you want me to be at the target? Where the casings are? Then you come up with idealized trajectory. Then you move this idealized trajectory as close as possible to the target, which is the green, let's say the green target, that green line that's coming as close as possible. And then you draw a circle on it like this. And this circle around the edges, you can drill from anywhere now to the target with the same constraints. Same kickoff, same passing through certain inclinations and the inclination at the target. So you draw the circle around the target. One edge will be your optimized trajectory. So you can actually play with it and come back with this circle. When you come back with this circle will actually look like this from the top. Around the edges, you can actually find out everything from which direction you can drill. Okay. So those kind of optimization, 15–20% of the cost, if you do it right. If you work for a big company like BP and Shell, they have a lot of iterations, maybe dozens of them to get here. And this is where small companies fail because they don't do this kind of hard work. The other I would like to show is the closed loop geothermal wells. You have two wells, 2 kilometers apart. They have side tracks meeting it and combining. One is injector, one is the producer. You can actually optimize where will you kick off, how far you will be, and the length of the horizontal part, and all kind of design you can actually do here in this software. And then you can feed this into the well engineering package and find out what will be the length, what will be the kickoff point, how to optimize, what will be the situation. So you can actually see the reservoir that you are meeting in. This is actually being implemented. Something like this is being implemented in Germany, according to my information. So I will show you maybe, because we are running out a little bit with time, but I wanted to also show you something else about the hydraulics. Suppose you have come up with a design. You can see on my right-hand side, you have a casing structure. This is 13 and 5/8" casing, and then everything is a liner. When you drill this final section, 6 1/8, what happens to the whole cleaning? It is showing you that you actually, sorry, I have to probably show you first the whole cleaning chart. The requirement to clean this hole will be 610, but you cannot pump that much because the strain pipe pressure will not cope it. And you can actually play with the software and solve the problem by changing the casing sizes interactively. You at one point you will be able to solve it. I'm not going to take too much time because we are a little bit running out of the time here. So I'm going to take you back to my slide pack. It is just to show you how you actually run this and solve the problem with the kind of base case. So let me come back to our slide pack again. Okay. So it will be kind of something that we would like to do with the software. Software is not for just simulation. They are actually to solve the problems. So just to kind of let you know that we will be offering a course. We have got few people already sign up for the course. That course will be only for 2 days in a week for 2 weeks, like only for 4 days, 2 weeks in 1 week. And maybe in the following week, we will take 2 more days and maybe offer this course as a practical training. That will be a one-off course. It's not gonna probably be repeated. I don't know, but that's the software-based. We'll be giving the software for 2 months, 2.5 months, something like that, so that you become master at the trajectories and everything. We'll be offering this maybe in coming months. We have not decided actually much about it, so we'd like to run this by you. If you would like to know more about it, please let us know. And now we come to the questions, and I'm going to open up the QA side of the things. If you give me just 1 second. And I'm going to open up the QA there. Okay. Just waiting for it to come. We got about 7 minutes, but we can ask some question. If we have more question, I will answer you definitely by the email. Question? I'm just posting it. Okay, go ahead, Damoon. Okay, okay, I will allow you to talk, my friend. Damoon, you can talk, my friend. Yeah, you can talk. Just unmute, please. Damoon.
Muted.
Yeah. You have to unmute yourself. Okay. Damoon, you can unmute. I have allowed it. Okay. Anyway, so let's come back to the QA and see who is asking what question. Okay, please, is the course free or paid? The course is paid because we have software, a very fancy software that you are going to get. And Dr. Thomas, Miyora, and myself will be teaching the course for the design and digital drilling. So these courses are quite expensive actually, but we'll be offering it at the lowest possible cost we can. So it will be something that we will add information. So please send me an email. I will speak with you later about this, but it will be paid. Yeah. Please ask, Paul. Okay, you are allowed to unmute. Sorry.
Okay, I'm unmuted. Just wanted to know, Naim, are you going to be in Vienna next week for the IADC Geothermal Conference and exhibition?
Unfortunately not, Paul, this time, because I got a couple of other things from other location. I'm getting some kind of project work.
Okay, no, that's absolutely fine. Have you anyone got any presentations there from Oxford Well Engineering or?
Yeah, we could probably talk about it because I know your phones. we can
talk
about it.
I will be attending, so I'll talk to you about it afterwards.
That will be fantastic, Paul.
Right.
Thank you very much. Okay. All right. Ask any question, anyone in this team. Okay, about the kind of knowledge sharing session that we have is actually mostly related to the workflow. each part of these workflows are actually could be expanded into the presentation. Geothermal is a passion that I have, and also Dr. Thomas Miyora also have it. That is why we wanted to have a software. Before we can say we can train somebody, we would like to train them to the level where they can perform and deliver a result rather than just going through slides and people may not remember 90–80% of it. When you do things, when you have a project, Mr. Thomas Miyora will give you maybe an example project which you will be running with all the way from start to the finish as a part of this course. So it will be a fantastic experience. I wish I had these kind of courses when I was growing up. I had to learn very slowly with very tough mentors in my time. Okay, and let's see who else wants to ask any question. Okay. So not anyone is asking any more question. If this is it, so okay, Patrick, how are you doing, Patrick? Okay, I will let you have a talk as well. So please wait for a second here, allowing your MIC. Okay, go ahead.
Can you hear me? Perfect. Hey, Naeem. So you were talking about the digital optimization as well, and one point there was that you need to have offset well data, of course. But I've seen in geothermal wells that there is often a lack of offset well data because the oil and gas companies, they keep that to their chest. So you need to then treat everything like a new exploration well. So how would you then tackle new like geothermal wells if you don't have the offset data of other known wells?
Yeah, you will go conservative. You will go conservative, upgrade everything, assuming that you have a monster to handle. For example, the ROP will be problem because you don't know if the ROP is going to be easy or not. The whole cleaning could be a problem. Then you will going gold-plated well design. It's going to cost you more, but when you have drilled the first well, you can improve things and remove the things that you don't really need. You will get a calibration point. But it is like anything else. If you don't know, you want to protect yourself from losing everything.
Yeah.
Okay.
And in your course, you will also go more into the detail of this or not?
Yeah, it could. Yeah, it could be done. Like you said, the well that I have designed had the same problem, by the way. What we ended up doing is this kind of approach. You will do everything just like it is, not like finding the hardest part. For example, let me give you an example. Suppose you are drilling in the blind area where the pore pressure and the fracture pressure is unknown. And now you have a problem because you cannot design the mud weights. You cannot design all kind of things. You may want to go for maybe the trajectory that's almost vertical or very close to vertical or less than 25 degrees. So you will design the well according to your challenges that you don't know of or unsure of. So I think there could be, and some of the information could be transferred over from oil and gas. There are some databases I know of. You can pay for the subscription. You will get something similar. Maybe you will try to history match or match it with similar wells elsewhere. Not in the immediate local area, but maybe outside, slightly outside. That will be your second best chance.
Okay. Thank you.
Okay. No problem. Hector, how are you doing, Hector? Let me unmute. Sorry about this problem here. Okay, you can talk just now, Hector. Unmute yourself, please. Yeah, you can talk. Just unmute, please. Go ahead. I can't hear you, man. Hector, or you can just type in if your MIC is giving you trouble. Okay. All right. So, yep. Yeah. Please ask question. Yes. Kuldeep. Okay, Kuldeep. Let's allow microphone. Yes. They can just unmute and talk, please.
Yeah, thank you. So my question is, does this course include the cement and mud design as well?
That will, I'll give you to Thomas. Dr. Thomas will talk about it. About the cementing, we can do modeling in the software. The software we have is very powerful. you can do a lot of things in similar to maybe that you would expect. And the fluid as well, because basically fluid is also the part of the well engineering simulation and designs. We do have the software. You will run sensitivities of various kind of rheological properties. Fluid is my favorite area actually, and you can design fluid to match. Yes. A short answer, yes.
Okay, thank you.
Okay. And if so I can, yeah, I think that Hector is gone there. So let's see who else wants to ask any question. So that's it, isn't it? Do you guys have any other question? Anyone wants to ask any question just about the course or whatever you would like to ask? Or shall we just wrap it up? Sorry, about 2 minutes over. I will give this back to Neil.
Okay, thank you very much, Naeem and Thomas. That was fantastic. Perhaps you can post the brochure, a little bit more information in the chat, and obviously things will be followed up. What I would just say, so I guess thank you very much for attending, everybody. And I hope you found the webinar informative and engaging. If you would like to learn more, similarly to Paul, or discuss any of the topics further, please feel free to contact either Naeem or myself via email or LinkedIn. So I can see you there, Thomas. Did you wish to say something? You are muted, Thomas.
Yeah. Mute.
No, not really. Just listening to you.
No problem. Okay, so all good. So again, thank you very much indeed. Again, if there are any questions at all, myself and especially Naeem and Thomas will be very happy to answer them once the webinar has finished. So just get in contact with us. Thank you very much indeed, and have a good day.
Same. Cheers. Have a nice one. Bye-bye.